Our first speaker of the day in this first session, which is going to be Roman time domain astronomy, is going to be Ben Rusholme from IPAC. And it'll be a joint talk too. So Jacob Jensen is also going to give the second part of this talk. So Ben, yep, whenever you're ready.
Okay. Well, hi everyone. I'm Ben Rusholme. I work at IPAC in the Keith Spalding building next door, and I'm going to talk on Roman and what's called a project infrastructure team, or PIT Rapid, that is based here at Caltech. And credit to Skylar for coming up with this an acronym, Rapid Alerts Promptly from Image Differencing. So I'm going to talk for around 25 minutes, and Jacob's going to follow me for 10 minutes, and then we'll have 5 minutes for questions at the end. But feel free to ask for clarification at any point should anything be unclear. Okay, so to give it its full name, the Nancy Grace Roman Space Telescope, for those of us who've been around for a while, has obviously a long history with various twists and turns. Originally, it was called right after its purpose, WFIRST, the Wide Field Infrared Survey Telescope. And it was the top recommendation of the 2010 decadal, and it became an actual NASA, for those of us who speak NASA project life cycle, became a funded phase A study in 2016, and in 2020 went into phase B, which is implementation. And the science case was refined over that time, but set at phase B, and is in this document you can find online with that reference that lists the objectives and the requirements for Roman. So it's a short document, but to paraphrase it, it has these 6 goals, and the main science goals for Roman are to investigate dark energy by a number of methods, and to do microlensing in the galactic bulge to look for planets. So time domain is not explicitly a top-level goal of Roman. It's implied in the supernova search, but the project office are very supportive of time domain. They want a lot of time domain to come out of Roman, but Roman, is going to be fabulous, but it's very different to other time domain experiments, missions, observatories that and so things are going to be a little different. So that's the main point of my talk, is just to talk really about what's the difference between Roman, CTF, Rubin, and how that affects how you approach the data and the alert stream coming out of the telescope. So to be a little more explicit, these challenges are listed here. This is just to introduce you to them. I will go into further depth later into the talk, but a lot of it has to do with the survey strategy. So ZTF, Rubin, and to some extent like TESS and Kepler, they work by having a very repetitive, very redundant scan strategy where you're just hitting the same field of the sky, the same orientation, same detectors at the same point again and again and again. And that makes image differencing relatively straightforward. It's never straightforward, but relatively straightforward. Spacecraft has completely different constraints, and Roman's going to be rocking and rolling all over the sky, and depending where you are in the sky, especially for the fields that we want to observe all the time, they're at the close to the ecliptic poles, so it's going to be rotating and it's going to be shifting. So that complicates things quite a bit in the analysis. It's not unsurmountable, but yes, I put this in here because Leo asked. First question Leo asked on the first day to me. When we stack images, it's a very complex composite of a number of roll angles and different detectors. So we produce a sort of composite PSF, which when we do the image subtraction, there's going to be residuals. So, we've been doing this for Rapid. It's all in the code. It's fine. If you wanted millimag precision, it's not what you want to do, but certainly for alerts and the precision that we need, it's completely fine. But be aware it's in there, and I know I'm just going to be talking about PSFs forever on this project. The second thing is, Roman is serving these very diverse science cases, and so there's multiple interleaved surveys. So the alert rate and the cadence coming out is going to be very, very variable, because we'll be looking high, and then we'll be looking in the galaxy, and then doing something else. And so if you're used to like a steady alert stream coming out of these experiments, like ZTF is just tiled the available sky every 2 nights, and we go around the sun, Earth goes around the sun, and so we do the entire sky over the course of the year. It's very consistent. I mean, it changes. Nights are longer in the summer. We go over the galactic plane, but it's, there's something every night. Whereas the Roman alert is just going to be very bursty all over the place. So, you're going to have to, look at the schedule and understand it when you're planning, when you want to do follow-up. The third is that latency was not considered in setting requirements. That's acknowledged and being looked at. The fourth is that the TOOs will be extremely limited. Because Roman has such a highly constrained sort of interleave survey, it's very hard to just suddenly go off and do something. So, there was in part of the cycle 1 proposal call that just happened, they did ask about TOOs. You could propose for that, but just be aware there's going to be a lot of constraints on it, and the expectation is you'll really to use something that's better matched than Roman. Saying that Roman will really trigger on things that are not well localized and that you specifically need the capabilities of Roman for. And the last one, which isn't really about sort of the fact that it's not time domain, but just to be aware, Roman is going to spend a lot of time looking at the galaxy, particularly the galactic bulge and even the galactic center. And that's going to be extremely challenging for image differencing. And also, it's just going to produce, just huge amounts of data, especially false positives, sorry. So, we're not yet, so my question sort of at the end of this session is, what do people want from the galaxy that's manageable? Because otherwise, it's going to swamp people. But as I said, Roman's going to be fabulous. It's a 2.4-meter telescope in space. The expected sensitivity is, the Roman docs are actually very good. I was reading them to write this talk. There's a table there, and that will give you all the small print and 2 decimal places. But roughly in 60 seconds to 5 sigma, it will see point sources around 24 dB magnitude. Varies a bit by filter, of course. It's 23 at the lowest, 25 at the highest. And infrared, as we all know, is wonderful for things like high redshift and also for things that are obscured by dust. And many things that are going a sort of cataclysmic end of life are surrounded in their sort of death shroud of dust. So it's particularly well matched to time domain. So I just put everything in one slice. It's necessarily condensed, but of course, we'll see lots of supernova out to high redshift. The expectation is a few dozen strongly lensed supernovae. Obscured supernovae will do well. Tidal destruction events, you tend to get UV, and then you see this infrared echo, which Roman will pick up. So, we should see a lot more tidal destruction events that are currently known. AGN variability, quick quasar flares, reverberation mapping. It's it helps to have that extra wavelength. And lots of stuff in the galaxy like nova, which are just shrouded. We'll see stellar mergers, kilonova, luminous red nova, and so forth. Okay, so from the requirements, what's the actual mission architecture? So as I said, it's a 2.4-meter primary mirror. It's the same sort of aperture as Hubble, but it's got a much shorter focal length, 8 versus 24. So it has relatively a very large field of view, 0.281 square degrees. Of course, that's very small compared to Rubin's ZTF, but for a space telescope, it's very large. It's 100 times, the field of view is 100 times the Hubble ACS. And there are 2 instruments on the spacecraft. The workhorse is called WFI, or Wide Field Instrument, and it's a 300 megapixel near-infrared camera out to 2.3 microns. And it's composed of 18 Teledyne Mercad detectors in this sort of crescent shape. You've probably seen the logo. And there's 8 filters, a prism, and a grism in front of it. There's a second instrument, which is a technology demonstrator, which is the chronograph, which is for searching for planets. There's actually a lot of colleagues at IPAC working on that, but for this time domain purpose, I'm not going to mention it, except to say there are discussions currently ongoing that we could parallel observe with WFI while the chronograph is observing, so that'll give us some deep drilling fields. This is all wrapped up in a spacecraft, which needs a Falcon Heavy to get to L2, so that launch is going to be quite interesting. And once it gets to L2, it's just in that semi-stable orbit, same as JWST in Euclid. And it's designed for a 5-year primary mission, with a possible extension. So due to the source of the mirror, there's been some sensitivity about, what images could be public. And, we've all been looking at this visualization from NASA. I looked it up, this was made in 2020. I've used this many times in slides. So there's been some images out of Goddard, but there's not been a great view. But fortunately, last week, Goddard put out a press release and a video. And finally, we got some great images. I was thankful we got some good images of what Roman actually looks like. So this is the internal part of Roman. This is what's called SKIPPA, the Spacecraft Integrated Payload Assembly. So there's obviously a lot of shielding and solar panels that go around this. It's called the OSD. But you can see here with some figures for scale, you've got the mirror at the front, the spacecraft bus at the back. This up here is the chronograph, and WFI is down here at the bottom. You get a real sense of scale. I believe the entire thing is, the entire assembled Roman is about 13 meters long and about 8,000 kilos. This is the actual WFI. I only had pictures of the engineering model, but this is the actual one. I found this image, and you can see these offset detectors, staggered detectors here. The gap, there's actually a readout. I don't know if you can see it in this. There's a readout on the edge of each chip, so that's why there's a gap to the third, because there has to be the readout at the side. And yeah, so project status. Again, for those of us who speak NASA speak, it's right at the end of phase D. The spacecraft's been assembled. It's gone through the whole usual Bevel testing, so thermal, vacuum, environmental, electromagnetic, thermal, acoustic, vibration. And there is a sort of Roman blog. I encourage you to follow it. I do by via RSS. And December last year, they announced that Roman was complete. They'd actually put the outer barrel over that skipper. And then just last week, they announced the Roman observatories passed final major pre-launch tests. I mean, there's still some testing ongoing, but quoting directly from that article, progress is well ahead of schedule. And this is remarkable given, it went into phase B in 2020. So COVID, shutdowns, everything. And so, massive kudos to our colleagues at Goddard who've kept, and it's now ahead of schedule. That's pretty unheard of for a mission of this class. And officially what we're allowed to say is mission is on track for launch as early this fall. So Nancy gave a month in the reception, which we're not supposed to say, but yeah, it's coming up fast. It's coming up fast. And so I'll be here before you know it. These are just some of the more assembly pictures. So this is the outer, solar shield, the barrel and the deployable aperture cover going on. And Goddard chose this as their sort of celebration photo of being finished. Of course, for us, this is the least interesting side. This is the rear of the observatory, but I suppose it looks kind of sciencey, and I doubt you can see anything from the other side because all the optics will be, of course, in this huge back roll. So, but yeah, Roman is done. It's tested. I mean, there's still many steps between here and L2, but as I say, it's going to, may hopefully happen this year. I was going to give a glossary, but then I thought, you'll have these slides for a reference. So this is sort of the Roman project organization, because you'll hear these terms. So it's run out of Goddard. That's where the project office are. The project scientist is Julie McHenry. They're responsible for the overall project management, WFI, and so forth. The chronograph was built by JPL. The WFI processing is done at the SOC, or Science Operations Center at Space Telescope. And for Rapid, that's our main interface, because we're getting what's called the level 2 data from them, which are the process frames. And then our output is being archived by MAST, the archive there. There's also the Science Support Center, IPAC, and a big shout out to them. That they have a lot of important tasks. They're doing the microlensing and the GRISM, CGI operations, and as you all know, from the cycle 1, they're doing the proposals. But under that, there's another level which are called the PITs, the Project Infrastructure Teams for WFI. And these were created in a call from 2022, and their purpose is to develop scientific infrastructure needed to address the mission objectives and support community science collaborations. And so they were selected in 2023, started in 24, and there were 5 of them. And the first 4 here all match, the stated mission objectives, but they added a 5th, rapid, for time domain. And that's us, and that's what I'm going to talk about for the rest of this talk. And one of our goals, so we're writing a pipeline, but we also support the community. There's things like special sessions with AAS, and like the big centerpiece was to have a community workshop. And the opportunity came up to partner with Hotwired, and here we all are. So I guess you all heard about that part. Rapid is a very small team. It's actually, even with the names here, we're running right now about 6 FTEs because most people are just a fraction of their time. And we're all very different to the other pits. We're all co-located in one place at Caltech. So we're just one of the 3 buildings close by here, either in the astronomy department, Cahill, or IPAC. And Mansi is the PI. And I'm very happy to, Azali just accepted a position with us, which I'm very happy about. I just put this in here for the record. Jacob will have some QR codes in his slide, but there's a number of ways to get in touch with us. Everything we do is public by SPP 41A, so you can look at the GitHub, you can look at the data. I just wanted to point out there is an actual Roman working group called Stride, which Ashish and Tyler run, meets the first Friday of every month, I believe, and if you want to register for that, just go to the outer space page for which you need a space telescope account. But yeah. Okay, so what did we promise to deliver? It was to be fast image differencing of every Roman image from a reference, an alert stream, source match files, force photometry, pretty much the same as ZTF. And we're following the classic workflow that all these projects do, where you have an incoming stream of images, you stack them to make a reference, a template, you subtract them against the image stream, you get difference images, do source extraction, you get candidates, you do a lot of filtering, classification, real bogus, and you put them into Kafka and you have an alert stream. And for these intermediate products, you can also use, you can do force photometry on the difference images and position matching on the catalogs to get light curves. And these are all very popular products in ZTF, and then we'll be doing the same for Rapid. So as I say, it builds on the ZTF experience. It's very highly automated processing. A lot of the architecture is the same, but we are running on the cloud instead of AWS. Given the prices for hardware right now, I'm kind of thankful about that. I would not like to be ordering equipment right now. But a lot of the code's been updated and written. Things that ZTF was written sort of 2015, 2016, so the state of the art has moved on. Operate right now, we're running in the Caltech cloud, but we'll be moving to the Science Mission Directorate cloud at ESMBC. All development and products are public. But we will, in operations, you're free to go and look at anything right now, but be warned they will change without warning. During operations, of course, we'll point you towards what we've validated and is suitable for use. We've been testing Open Universe 2024 simulations. I'm kind of sick of them by now. We've rerun them so many times. But they've been very valuable. Thank you to Troxel et al. And if you want those simulations, they're actually held in Ursa next door. We've added source injection. This is new from ZTF. So we can evaluate reliability and completeness. If you have a favorite source, let us know. We'd love to add more things in. So yeah, this image differencing pipeline, the simplest form, has been up and running since 2024. We've been just iterating on it again and again and again, and slowly adding and improving things. And we're this close to being fully done all the way through to alerts. We've done force photometry, we've done light curves, and we're making alerts, but it's just not quite all fully integrated yet. Yeah, so our deliveries, we will be, making files. I did talk to someone from Link. We're already making hats for our light curves. I think the hot things will be held within the Rapid cloud space, but ultimately things will be delivered to MAST. We're negotiating with them right now. My hope is that we'll have fairly regular, because we're not doing like big data releases as such, so we'll just be rolling things up. I would like to do it monthly, so it's fairly regular, and deliver them to MAST where you can actually access them, and also access them through the Roman cloud, which is called the Roman Research Nexus. And we have force photometry running, but we don't have the interface yet. And my preference, this is the first Gisella's heard of it, was that we'll create some service with an API, so you can call it yourself from your own Nexus account and use your own credits, rather than having a centralized system, which becomes very difficult to manage. The alert schema is under active development. You have some alerts, for the hackathon. We started close to ZTF, but we veered over to Rubin. There's a lot still to add. We got to fold in some of the real bogus work, Star Galaxy, Force Photometry, Gaia. There is obviously external data sets coming that we don't have access to yet, but we will add them as they come available. And we can imagine lots of things as the survey progresses, and we get better knowledge of the sky in the fields, that we can add like photoz's and links to spectra, things like that. A little of the survey, this will come up several times, but yeah, the main science surveys are called the core community service surveys. And for time domain, it's obviously the high latitude time domain is the one we're mainly interested in, but there's lots of interesting things in the other surveys. This is, we just got a schedule from Gisela and the SOC. Thank you very much for that. And we're sort of digging in and beginning to model the mission and understand, what's our stacking strategy and differences and counts and so forth. But this is the distribution of the sky in our own deck. But it gets very complicated when you dig in. This is how the different surveys are interleaved, and the high latitude time domain survey actually doesn't start in earnest. There's some sort of pre-fields and there's some fields at the end, but it doesn't start to the central 2 years of the mission. And it's mainly, the schedule is mainly anchored by the visibility of the galactic bulge. So if you just take that and extrapolate it as to what the alert rate is, making some assumptions, you see these huge bursts, which are the galactic bulge, and it comes out at 12.5 billion alerts for the 5 years, which is a lot. And if you got alerts the same size as Rubin, it's actually 3/4 of a petabyte total. So one of my questions at the end is, what do we want from the galaxy? Do we want things like image cutouts in the alerts? Because if you just extrapolate, everything is identical. 3/4 of the alerts are the galactic bulge survey. So again, on just differences, just be aware, targets of opportunity will be very limited because of the constraints of the schedule. There's only going to be up to 4 a year, and it will take a couple of weeks to schedule them. So, you can't get on anything very fast. There will be discretionary requests for truly exceptional events. But yeah, again, you've got to make the case that they're done from Roman. It's got to go past a lot of review. Right now, because this comes up a lot, the latency requirement for the data from the spacecraft to level 2 is 48 hours. And spacecraft is never going to be as fast as ZTF or Rubin. It's got to downlink, but Roman does not use the DSN, and this is died. Can we go back? Okay. It's using a dedicated network of dishes. It has to get like 1.4 terabytes back from L2 every day, which is 6 times greater than Euclid. But yeah, the SOC are aware of this. They're benchmarking, but right now they don't have an accurate number. Their requirement is 48 hours. They hope to do better than that, but they can't give us any information right now. And then, yep. And yeah, as I said, the galaxy will be extremely challenging. So I'm interested to know, get people's opinions on what would be valuable and what will be essential in that part of the survey. Okay, so we've been working on this for a long time, and you'll be talking, from the decadal surveys about this new era in astronomy, And, it's finally almost here. Euclid launched 2023. The Euclid DL1 data will be out in October this year. Rubin, very nicely started producing alerts last month. Roman, will launch this year, hopefully. Commissioning is 90 days, and we have a commissioning activity request in. The early commissioning, of course, will be a lot of calibration, but we have a request to do some fields to practice image differencing. And so, yeah, Roman alerts will be coming soon. Okay, I'm going to pass on to Jacob.
So there's been a water spill here, so people just be careful of that. We're going to get it taken care of.
All right, great. And this died, you said? Yeah, okay. Okay, so I want to take you all on a little tour of the pipeline development that we're doing, get into a few more of the gory details, maybe whet your appetites a little bit for the hack session if you want to, dig into any of our data products, and actually, get your hands a bit dirty there. So Ben already showed this. Of course, this is our sort of main overview of the pipeline, and our GitHub is public, like Ben mentioned, and you can also look at our read the docs, which are again constantly evolving and changing. And we're happy to take feedback as we continue development. Right, so let's talk a little bit about reference images. Ben mentioned this already, right? But Roman doesn't have a fixed grid on the sky, and so when you build a mosaic or do difference imaging, you have to deal with these different roll angles and different detectors of the 18 of the entire WFI that may contribute to your mosaic and make complicated PSFs where it's different over here than over here with discrete transitions depending on which images go into any pixel of this mosaic. So this is an example of a mosaic of 100 frames, just sort of as an example. And we're using a code called AwakeGen, or iCore is another name for it, which was developed as the WISE co-adder for the WISE and NEOWISE missions at IPAC. So that's what we're using to build these mosaics. And then here, this is just an illustration of the way we've decided to tile the sky. So we're using the SOC sky map tessellation, which are these blue squares here. So each one of these blue squares is one of our fields. And then the reference image here in cyan for that square is oversized. So it overlaps with the neighboring field so that, a given science image that comes in, you want to do subtraction, it may be rotated or offset with respect to that image. But the reference image is big enough that you don't lose any coverage in your incoming science image. And then, you can imagine here for your force photometry, say there's a transient here. In this instance, it got tied to this field with its reference image. But in another instance with a differently oriented science image, it may get tied to this field and then have a different reference image. So that's all things we have to take into account in development, and also that users will have to be aware of, when they're looking at the force photometry and the alert stream on all of our products. So just wanted to bring that up. Of course, talk about difference imaging. So we fully implemented 2 different strategies that are integrated into the pipeline, both for batch testing. So right now we run both of them. One is Zogi, which of course was used by ZTF, and then a newer implementation or a newer algorithm called SFFT, which does kernel matching in Fourier space. And so it's kind of we're doing it on top of a Zogi-like PSF cross convolution, and then running the kernel matching to sort of refine any mismatches in the PSF or small spatial offsets. And so, right now, both of these are working in our pipeline, and SFFT is also the one being developed by members of the Supernova Pit, and, is being used for their difference imaging as well. And so, like I mentioned, both of these are fully integrated, so we can test them and sort of continue to do iterative development and improve things. And, but both of them were successfully recovering sources in extragalactic fields. So, here's an example of real pipeline output from both algorithms on the same field of a transient that went off in this galaxy here, this is an open universe transient from those simulations. And you can see, even for these faint events, we can recover them both pretty well. Okay, so I want to talk a little bit about source extraction. Of course, when you do difference imaging, there's going to be various kinds of artifacts in your difference images, which get pulled out in your source catalogs. So we're adapting a strategy sort of akin to what ZTF did to do tiered filtering. This is one example, the elongation of your source. You can use to distinguish, get rid of most of the garbage here in gray and try to, zero in on your true positives that are, high signal to noise. So this is working quite well. And it's also been work that an undergraduate we've been working with since last summer, Alice Chiobanu here at Caltech, has been doing a lot of work on both for sort of parallel filtering streams for S extractor detection catalogs, as well as with photutils, an implementation of the DAO Starfinder algorithm. So if you want to play with any of this, again, there's hackathon tracks. I've color coded them, but if you want to grab your sticker later, just ask one of us which color you should grab. Okay, next slide. Okay, and then, of course, once we have nice filtered catalogs, we can also turn to machine learning to do real bogus scores that will be part of the alerts, and then, send out the alert stream. And so, of course, like I mentioned, there are lots of different kinds of false positives we run into. Here's a example of a particularly bad looking stellar residual, or maybe you had a slight astrometric offset and a galaxy gives you sort of this extended sort of emission here. But again, the machine learning models, in addition to the sort of pre-filtering we're doing, will hopefully help find the gems in all of this, all of the candidates, and produce a relatively clean and filterable alert stream. And so, see, I keep forgetting how to advance. Right. So we'll of course stream the alerts containing data for time variable sources. This will include cutouts, photometry, history if there's previous observations of that field, the real bogus scores, of course, and then they'll be distributed for brokers to pick up, and then of course for the community to analyze as they wish. So that's all of you. Right, here's an example of, again, the type of data that will be in the alert packets. You'll have things like cutouts. This is, again, a real example you can sort of play with in the hackathon if you want to. And then, for this particular detection, there were all these previous detections in the light curve of this transient that you'll have that light curve history in your alerts as well. Okay. Right, so I want to give you a little bit more detail on the testing we're doing. So we've mentioned a couple times we're using the Open Universe 2024 simulation. So again, big thanks to Troxel et al. These have been really helpful. We're currently using, there's sort of a set of post-survey data at later MJDs, which have a different set of sort of random transients in them, but they're relatively clean for the transients included in Open Universe that we're trying to detect. So we use those to build our references. And we're currently running tests on 13 of those fields that have good reference images with at least 6 to sort of 12 images. But in the data set for each of those fields, there's still something like 1,000 images per filter. Again, for the 7 filters that were included in the sims. And so there's 10 million individual instances of transients that were included in the Open Universe simulations in this data set that we've been processing. I will say the vast majority of these are probably sub-threshold, down at 28, 29th magnitude, but they are injected in there. So what we're doing on top of that is injecting additional point sources, sort of with randomized offset from galaxies or other detected sources in the images, so that we can have better recovery statistics at bright magnitude. So these are not astrophysically realistic transients. They're just sort of random from image to image. But again, we're using them to do detailed recovery statistics there. So of course, image differencing is a complicated multi-dimensional trade space. We can select our algorithm, we can use different source extraction on the difference imaging products, we can modify our filtering strategies, and then of course on top of that you can add machine learning, and all of this depends on the filter. May depend on the magnitude of the source you're talking about, the density of the stars or other sources in the field, and all of this, of course, is dependent on the details of the PSF and, the complications we talked about in the reference images. So there's a lot of interactions between these components. So, kind of the way we're trying to optimize this, we're thinking about this systematically. We can sort of remove most of the false positives with this filtering while we try to maintain high completeness. But we're sort of in the process of defining a rigorous figure of merit that will, primarily be optimized for recovery completeness at a allowed sort of tolerance for false positives. And then also, prioritizing things like photometric accuracy and, sort of the quality of the difference images overall. So, here's an example of this, the sort of cumulative distribution of sort of detections in our catalogs as a function of magnitude. You can see there's a lot of sort of junk here, but even the filtering before real bogus gets you down from over 1,000 to image to something like, maybe 10 or a few tens. You can sort of pick whatever false positive threshold you want and then define a signal to noise cut or something that, limits your false positives. And again, the real bogus scores will be incorporated into this as well. But we can, achieve relatively high completeness down to, 24th, 25th, 26th magnitude, even picking some things up, and, are achieving reasonably good photometric accuracy as well for our injection. So, this figure of merit, as we continue to sort of finalize it, will be the primary criterion then for the sort of experiments we can do sort of before launch and also with injections in science operations data as well to make the final down selections of the difference imaging algorithm and all of the parameters and other things we're including there. And I realize I'm going long, so I'm going to go quickly through the last few slides. Ashish Mahabal, who's here, is sort of leading our machine learning efforts. And this is highlighting some work, again, of a student who's been working with us, Karen Gandhi, who I think this paper was submitted today, so you should check it out if it becomes available on arXiv. But we have a convolutional neural network that's doing pretty well against some other sort of industry standard or popular models. And we're also looking into this idea of domain adversarial training so that we can sort of adapt the models we train on injections and sort of pre-launch to also do well on the real data and the real sources. And so if you want to hear more about that, definitely tag up with Ashish. We're also injecting variable stars with light curves now. And we are just doing some batch runs with these. And we're preparing for the GBTDS as well. So these will be very challenging fields with high stellar densities. But we're getting sort of decent subtractions out. And we're working with Robbie Wilson, who's helped us inject some additional variable stars there with sort of like outburst-like properties. So here's an example of that. And his sims, RimTim sim, have been very helpful for us as well there. So I'll just leave up a summary again with our sort of deliverables for Rapid and remind you that Roman is launching as early as later this fall. So it's time to get excited and prepared for the alert stream that will be coming. Thank you.
All right. Thanks, Jacob and Ben, for the nice talks. Let's see if there's any questions. We have like 2 minutes. Leo.
Hey, Jacob. So how many transients could you miss because they coincide with a subtraction artifact? Or maybe a related question, are there particular, potential host galaxies that, just frequently have bad subtractions that would mask the presence of any transient?
Yeah, that's a great question. And so I think at least the biggest sort of thing we're dealing with at the moment is, residuals in the core of galaxies that can be quite bright and sort of look and be, look a lot like a transient. So I think that's sort of what's driving the sort of recall. In the machine learning table I showed, the recall was maybe like 70%. I think that's probably driving most of it. So yeah, it'll be really trying to improve the subtractions in the cores of galaxies. That could be one of the biggest factors there.
Thanks.
Oh, back there, Monica.
Hi, very nice talk. Jacob, I was just curious, have you explored the Allard and Lupton difference imaging method as well?
We haven't implemented it specifically, no. And SFFT, I mean, is in that family in that you're, running a sort of kernel matching algorithm to derive the kernel to convolve the template. But it has some differences from the Allard and Lupton. So we haven't tested it specifically, but like in that family, yeah, we're going with the SFFT.
Okay, and one last question. So the template, maybe I missed this. How are you generating the template? Is it from the science frames themselves or?
Yes.
Okay. Gotcha.
Yeah, we're mosaicing science frames with the awake gen code I mentioned, but yeah, sort of the first images that come in of a field will become the template for, the rest of the field.
All right, let's thank our speakers again. Sorry for the truncated question and answers. You can save them for the discussions.